Okay, so let's get started on a chapter concerning photovoltaic systems. Photovoltaic, the word photovoltaic refers to the direct generation of electricity by solar irradiation. What we're first going to do is just take some time to look at the fundamentals behind photovoltaic cells. So in this case, atomic theory and semiconductor theory are good places to start an examination of the operation of these systems. So in an atom, the number of protons is equal to the number of electrons, and that number is called the atomic number of the element. So in silicon, the valence bond is partially filled and contains 4 electrons. It must contain 8 electrons for that valence band to be filled. If electrons in an unfilled valence band are lightly bound, they may attach themselves to a neighboring atom, which gives that atom a negative charge, resulting in the donor's atom becoming a positively charged ion. Electrons in the valence band can become so energetic that they jump into a band that is far removed from the nucleus. This remote band is called the conduction band. So the difference in energy between an electron in the valence band and one in the conduction band is called the band gap energy. Electrons from the conduction band require only a small amount of energy to move away from the atom, and this is responsible for heat and electrical conduction. This table gives you an idea of the representative photovoltaic material band gap energies, starting with silicon at about 1.11 electron volts, all the way up to indium phosphide. So these band gap energies, the units are usually expressed in terms of electron volts. So insulators, for example, are materials whose atoms possess full valence bands and have high band gap energies. Conductors are materials whose atoms have relatively empty valence bands. Materials whose atoms have relatively full valence bands are semiconductors, and those have band gap energies less than 3 electron volts. So silicon is an example of a semiconductor. It has 4 electrons in a valence band. Pure silicon itself is called an intrinsic semiconductor, but if a small amount of impurities, usually called the dopant, is combined with the pure silicon, an intrinsic semiconductor results. You have 2 types. You have an N-type semiconductor results if the dopant has more electrons in the valence band than the base material. An N-type semiconductor seems to have an excess of electrons, even though the semiconductor is electrically neutral. And then there's the P-type semiconductor, which results if the dopant has fewer electrons in the valence band than the base material. The P-type semiconductor appears to have a deficit of electrons or an excess of holes, although it is electrically neutral. The reason for doping a pure semiconductor such as silicon is that a junction is formed with N-type and P-type semiconductor materials that enhances the flow of electrons and holes. So this diagram gives an example of a PV cell. This PV cell is shown as a PN or a P-type and N-type, or what they would call a PN junction, with an incident photon. So I have a photon coming in, or sunlight. An external load is connected. So if the incident photon is energetic enough to dislodge a valence electron, the electron will jump to the conduction band and initiate a current flow. For an electron to be forced in the valence band to the conduction band, the electron must possess at least the band gap energy. So to quantify the energy of a photon, you would go ahead and take Planck's constant, h, which is defined as 6.625 times 10 to the negative 34 joule seconds, and you would multiply that by the frequency of the photon. The frequency of the photon can be quantified by taking the speed of light and dividing it by the wavelength of the photon. do a quick example problem. This problem is asking you to determine the wavelength of light that corresponds to the band gap energy of silicon. So if we were to start off this example problem and try to compute what the wavelength is, we can combine the two equations from the prior slide and end up getting that if we take Planck's constant, multiply it by the speed of light, and divide it by the band gap energy, we would end up with the following. Take the Planck's constant, multiply that by speed of light, which is 3 times 10 to the 8th meters per second. Divide that by the band gap energy, and of course we have to go through the conversion where 1.16 times 10 to the negative 19 joules is equal to 1 electron volt. So in that case, we would get that the wavelength is basically 1.12 micrometers. So again, that's looking at the wavelength of light that corresponds to the band gap energy of silicon. So it kind of gives you an idea of what the wavelength needs to be in order to have enough minimum energy to dislodge that valence electron. This example problem has important implications for the operation and efficiency of photovoltaics. So photons with a wavelength greater than 1.12 microns contain insufficient energy to dislodge a valence electron in silicon. Hence, photons with wavelengths greater than 1.12 micrometers will induce no photovoltaic effect in the silicon. Photons with a wavelength less than 1.12 micrometers possess more energy than is required to dislodge a valence electron in silicon. But however, a single photon can dislodge only a single valence electron. And the difference between the band gap energy and the photon energy is absorbed as heat by the photovoltaic cell. So basically, it's saying that anything that has less than 1.12 micrometer wavelength that has more energy necessary to dislodge the valence electron just results in heat. Here's a graph to kind of help illustrate that effect. On the y-axis, we have relative intensity. On the x-axis, we have wavelength. And so you can kind of look at this as sort of the range of wavelengths that you could see in incoming photons. Again, anything greater than 1.12 micrometers has insufficient energy to dislodge the electron. Anything less than that has excess energy. So in that case, there's going to be extra, basically heat that's going to be dissipated for all wavelengths that have less than 1.12 micrometers. So the notation E sub 1.12 represents the energy required to dislodge a silicon valence electron. So then the equations that we just looked at can be converted to ratio form to express that portion of the energy required to dislodge a valence electron for a wavelength lower than 1.12 micrometers. And the excess energy then becomes the difference between the actual energy minus the energy required to dislodge the electron. So that's the smaller the wavelength, the greater the excess energy of the photon. So the generally low efficiencies of photovoltaic devices are attributable to this principle and to additional, of course, additional conversion efficiencies associated with photon wavelengths less than those corresponding to the band gap energy. So this graph kind of gives you an idea between the theoretical and measured efficiencies of photovoltaics and the different materials in photovoltaics. So we concentrate here on silicon. We can see that the maximum theoretical percent that we'll look at is about 24% efficiency, where we have measured efficiencies of 18%. And similarly, you can see for other types of photovoltaic materials, you can see their theoretical efficiency compared to their measured operational efficiencies. This graph kind of gives you an idea of how efficiency has been affected. Efficiency of photovoltaics changed over time. So on the y-axis, you have percentage of efficiency, and on the x-axis, you have a time scale from 1975 through 2010. You can see that overall efficiencies have increased over time. One strategy used to overcome these low efficiencies of solar cells is to provide more than a single junction. That is to fabricate two or more junctions, one above the other. Recently, these multi-junction photovoltaic cells have shown some impressive increases in efficiency.